The generative function for the Bessel function of first kind is given this. This can be expressed or can be expanded in terms of a series of Bessel functions, where the Bessel functions are the basis of this expansion. The objective here is to develop the expression of the Bessel function from this generating function. Now, to do that, we need to expand this generating function, and we separate it into two exponential. The first one is obviously expanded in this way, while the second one is this. Combine these two and substitute these two equations, 3 and 4, into 2. We will get the new formula in terms of the expanded Bessel function. So the left-hand side of equation 2 becomes in this form. And if we replace the summation index n by p plus m, this means that the new running index will be p instead of n, and will go from minus m to infinity, because if we put n equals 0, then the new running index starts from minus m, and if we go to infinity, it means the final running index is infinity. Okay, so the range of summation now for p becomes from minus infinity to infinity as a result of that, while the summation over m runs from minus p0 to infinity. Also, for a given m, we have t to the power p, as p greater than or equal to 0 goes from n equal p plus m. However, the generating term here becomes like that: t to the power p plus m instead of n, over the factorial instead of n factorial, we get p plus m, and here we're going to x over 2 over p of m, and the left remain as is. The coefficient of t to the power p, however, in equation 2, can be equated on both sides, or to both equations 2 and 6, to get jp equal to this. And that's what we wanted to prove. Here we're going to use the generative function to get an integral representation of Bessel function. To do that, we substitute t by e to the power I theta into this equation to get this form. Obviously, the exponent here turns out to be e to the power I x sine theta. We're going to expand the right-hand side of this equation up to the fourth order. Doing this, we'll get j minus 4 e to the minus 4i theta plus etc. etc. So the index runs from minus 4 to 4, and we got these 9 terms. From equation 3, we're going to factor out these two terms, and these two terms are nothing more than j1 of x multiplied by these exponentials. Here, because when n is integer or p is integer, we have j minus n is equal to minus 1 to the power n jn of x. That's why we got this minus sign in here, in this one. and we replace j minus 1 by minus j1. Okay, and then again we will pick, this will be of course transformed to 2I j1 sine theta. Okay, again in the same way we can get from equation 3 j minus 2 e to the minus 2I theta plus j2 of x e to the power 2I theta. Similarly, we can find that sum of these two is nothing more than the 2j2 cosine 2 theta. Again, we'll do the same thing for the third order and the fourth order. So in the third order of n equal 3 will give us this, while the fourth order give us this. By collecting the terms obtained in equations 5, 7, and 8, together with 9, and substituting all those into equation 3, we'll get this form. So e to the power I x sine theta is going to have even terms and odd terms. Writing e to the power I x sine theta as cosine of x sine theta equals plus I sine x sine theta, and we equate equation 11 with that with equation 12, we'll get these two expressions for cosine x of sine theta and sine x of sine theta. Now you need to multiply equation 13 by cosine q theta, integrate from 0 to pi to get this, and use the orthogonality relation. So this will reduce this expression, second on the right hand side of this equation 15, into pi j2. Okay, and in this case we're going to get j2 equal to 1 over pi multiplied by this term. So to generalize, we can put p equal q, and jp is going to be cosine of p theta cosine of x sine theta when p even, and jp equals 0 when p is odd. In a similar manner as before, we can get an expression for jp as well from 0 to pi sine p theta sine x sine theta when p odd, while that equals 0 for p even. Now combining all these for even and odd values of p from equations 18 and 20, we can obtain a global form for jp of this form. Of course, this is nothing more than the expansion of cosine p theta minus x sine theta. So the term in equation 23, the integrand is can be expanded to get this one easily. Now if you take special case for p equals 0 of this one, we're going to get j naught equal to cosine integral of cosine x sine theta d theta. If we look at equation 24, we're going to see that the integrand cosine x of sine theta repeats itself in all four quadrants. So if we make the integral from 0 to 2 pi, while the integrand sine x sine theta, if we're going to put the limit from over one cycle from 0 to 2 pi, we can see that the sine of x sine theta reverses its sign in the third and fourth quadrants. That will give this one a value of 0, while retain the cosine integrand in equation 24. So from equations 12 and 25, we conclude that J sub naught, or J naught, is 1 over 2 pi over full cycle of e to the power x sine theta d theta. This equation usually used in the theory of diffraction for a circular aperture. And the integrand that represents the amplitude of diffraction looks like this one. So somehow this part is somehow related to something like this as an application to